Alright. Alright, y'all, we are going to get into chapter 11. So chapter 11 is going to cover gases and gas laws. First, before we talk about gases and gas laws, you've got to understand what pressure is. So pressure is really just the hitting of gas particles along the surface of a container that's containing those gas particles. That's really it. And so it's just based on collisions. That's the main thing. And the surfaces that the particles are colliding with. Now, this part of the textbook is going to kind of try to explain to you like how a straw works. How a straw works is that there's constantly atmospheric pressure, so PATM is P atmospheric pressure, pressing down on everything. You, me, liquids, everything. Atmospheric pressure, the air pressure is pressing down on. Now, when we relieve the pressure inside the straw by creating a vacuum, then we allow the atmosphere, the outside of the straw, to be greater than the atmosphere inside or the pressure inside the straw. Therefore, the atmosphere pushes the liquid up into the straw. So that's kind of how that works. So you have to maintain that you couldn't have a very large straw like this because it wouldn't work. You'd have to have way too much atmospheric pressure in order to get this to go up. That's all this is really talking about. You can do it with a vacuum pump, or you can do it where you are creating a vacuum by sucking on the straw. Kinetic molecular theory, we can break that down into different parts. So kinetic meaning what? Kinetic meaning the energy of movement, right? And then molecular meaning, well, molecules. So kinetic molecular theory is the theory of the movement of particles. You can click on this link here. Unfortunately, I can't show that to you because it's a flash, and so I can't use that on my iPad to show that to you, but you can click on that and go through that simulation. It's like an animation. It's helpful. But essentially, we need to look at 4 different postulates for the kinetic molecular theory. First, the particles need to be in constant motion. So these particles over here are constantly moving. That's denoted by the swoosh marks behind the particles here. The second one is that there are no attractions or repulsions between the particles. So when they hit like billiard balls. Okay, they don't stick together, or they don't actually repel each other. They just kind of hit and they transfer their energy to the next particle. This is called an elastic collision. Okay. Then we assume that there's a lot of space between the particles compared to the size of the particles themselves. The volume of the particle is so small in comparison to the volume of the space where the particles aren't that we said the volume of the particles is essentially nothing, essentially zero. That's what that postulate means, that part of the kinetic molecular theory. And then the last one is that the speed of the particles increases with increasing temperature. So the average kinetic energy is directly proportional to the temperature in Kelvin. It's really important. So if you remember Kelvin, degrees C plus 273.15 is equal to your temperature in Kelvin. And every time we're doing gas laws, every time you see a temperature, you're going to have to change it to Kelvin for these laws to work, because it's part of the theory that underlies all of the mathematical laws that we're going to talk about. That's this model. So a couple other things about gases that we need to know. Gases are compressible. Because there's this extra volume, right, this extra space between the particles, we can push down on that. We can smush the particles together a little bit and compress a gas. Liquid, there's not a whole lot of space between the particles, and so you can't really press down on that very much. To show you really kind of how that space works out, if you take the same particles in 1 can of soda liquid and you turn it into a gas, it would be 1,700 cans of soda. So that's a big expansion when you turn something into a gas. So when you think about just boiling water, like you're taking that water, maybe 1 soda worth of water, you're turning it into the volume of 1,700 cans of soda worth of water. So that's a big expansion, so we need to really consider that with the space between the particles for gases. Alright, going back to pressure, pressure is simply the force over area. And so think about like pounds per square inch, PSI is what we measure our tire pressure in. And that's just how much force and how much space. If you wear high heel shoes or you wear shoes that are a little bit smaller, maybe they've got a heel on them, then you're gonna feel more pressure on your feet because you're not moving the force of your body around a larger area. Um, that's why elephants' feet are like very flexible and like why they're padded is because there's so much force that the feet have to hold. Their area needs to be very large in order to maintain a lower pressure because a higher pressure is painful. Um, Same thing happens in your ears, and so your ears are trying to maintain um, pressure equality, and when we can't allow that to happen, or because we move into low pressure areas too fast, like up in the mountains or up in an airplane, then we get this higher pressure situation inside of our ears, lower pressure outside, and that causes our ears to feel weird, and we have to want to press. We want to like relieve that pressure. So that is kind of more what pressure is and how it kind of relates to us. And just some more images showing you kind of what conditions would have lower or higher pressure. Less particles would have lower pressure, more particles would have higher pressure. All of the units of pressure. Pressure comes in a lot of units. The conversions that you need to know are right here, these two. You may use this one sometimes, but you really need to know these two. PA is for pascals. ATM, that's the one we're going to use a lot. That one is atmospheres. So if someone said, hey, let's just say whatever we are at, normal atmospheric pressure, we just call that 1 atmosphere, and that way all our math is easy. That's where that comes from. Millimeters of mercury is literally measured by a barometer. And we have one in the lab. As the atmospheric pressure presses down on the barometer, the mercury, liquid mercury inside the barometer goes up. And how far it goes up is actually measured in millimeters. So that's millimeters of mercury. 1 millimeter of mercury is equal to 1 torr. I'm not sure where torr comes from, but you should know that. And then you've got PSI, these other conversions here, but these are the ones that you should know. Here's another list of these. Note that the 760 is exact. That means infinite sig figs. So let's do some quick math. 0.311 ATMs, millimeters, ATM 2 millimeters of mercury, so I'm going to use this conversion. 1 ATM is equal to 760 millimeters of mercury. That's my conversion, right? Cancel at ATM, and I get 0.311 times 760, 236 millimeters of mercury is my answer. Alright, so when you're on an airplane, you experience these pressure differences. They say if cabin pressure decreases, then the oxygen masks are going to come down, right? That's just because, pressure is something that we have that's very helpful to know about, and is something we experience in our daily lives. So, gas laws. Your book has a whole bunch of these. You don't need all of them. So I'm going to go through them, and then don't want you to write anything down yet. Boyles Law talks about volume and pressure. The volume and pressure are inversely proportional or indirectly proportional. That means if one goes up, the other goes down. So think about it. If I've got a pump, right, if I increase the space for the gas, the pressure is going to decrease because there's more room, so they're not going to be pressing up against the walls of the container. If I decrease the volume, though, there's less room, so there's going to be more pressure. So that's inversely or indirectly proportional. Charles's law relates volume and temperature. So if I increase the temperature, like in this hot air balloon, then I increase the volume of the gas, right? Because they're moving faster, they're moving further apart, and so the whole volume of the gas is going to be greater. That's directly proportional. Avogadro's law is a direct proportionality between volume and moles. If I increase the moles in this balloon, the volume's going to increase because I'm putting more gas in it. So that really makes sense. These are very common sense kind of things. Now here's all these laws. If we put them all together, we get this. This is a direct proportionality sign, but I can't really use that in the math, right? I want an equal sign to use in the math. So I put in this proportionality constant R to give me this equal sign, and then voila, I have the ideal gas law. PV equals nRT, or piv nert. The R for piv nert is 0.0821 liters times ATM over moles times Kelvin. This is a unit. It is not something to plug in. This is a unit. You also need to make sure that your volume is in liters, your pressure is in ATM, your moles are in moles, and your temperature is in Kelvin for this one to work, because you can't use this R with different units. Now, the other one you need to know is called the combined gas law. It's all the ones we just talked about: Boyles, Charles, and Avogadro's. Another one called Gay-Lussac that's not in your textbook, but that's where the V and the T comes from. Or, sorry, P and T come from. You're going to add in an N. We're going to add in Avogadro's law here to make a true combined gas law. So, if you remember these two laws and R, that's all you need to know for this whole chapter. That's just all your gas laws. So let's put that into action. So a sample of a gas has an initial volume of 158 milliliters and a pressure of 735 millimeters of mercury and a temperature of 34 degrees C. If the gas is compressed to a volume of 108 milliliters and heated to a temperature of 85 degrees C, what is its final pressure in millimeters of mercury? Okay, so we can go ahead and start working this out. What I want you to do first is to bring out all of your variables. So we've got volume is equal to 158 milliliters. Then they tell me I have a pressure of 735 millimeters of mercury. Now I don't know if I need to convert this yet. I'm not sure what equation I'm using. They tell me a temperature 34 degrees C. Now, every time I see a temperature, I'm going to change it to Kelvin. Every time. So I'm not even going to wait and see what kind of equation I'm using. I'm just going to go ahead and add that 273.15. And I get 307.15. And I'm going to remember that this 7 is significant. Alright, now the gas is compressed to a volume. So this is a new volume. So if a second you have more than one volume, the old one becomes 1, the new one becomes 2. Everything that goes with the old volume is now also 1. Okay. This new volume is 108 milliliters. They tell me it's heated to a temperature, so this is a new temperature, 85 degrees C. I'm going to add my Kelvin, 273.15 plus 85. 358.15 Kelvin. Again, the 8 is significant. And then they say, what's the final pressure in millimeters of mercury? Now, I don't have to change my volume as long as both of them are the same. And I don't need to change my pressure because they're asking me for millimeters of mercury. The only thing I do have to change is I have to make sure everything is in Kelvin, because that comes from the kinetic molecular theory. Alright, so let's think about what equation we're going to use. Well, if I've got multiple P's and T's, I'm going to use the one that has multiple P's and T's. The combined gas law has multiple P's and T's. I'm going to use that one. So let's write out the ideal gas law, or sorry, the combined gas law. Okay. Now we didn't talk about N, we didn't talk about moles, so we can just erase moles. Just erase it if you don't have that variable. The next thing I'm going to do is cross multiply. So I'm going to say P1 V1 T2 equals P2 V2 T1. They asked me for P2, so I'm going to say P2 is equal to P1 V1 T2 over V2 T1. Alright, so I like to rearrange these with the variables before I put the numbers in, because it makes more sense for me. You can put the numbers in if you want to. If it works for you, it works for you. So my P2 is going to be equal to P1, which is 735 millimeters of mercury, times V1, which is 158 milliliters, times T2, which is 358.15 Kelvin, divided by V2 is 108 milliliters, And T1 is 307.15 Kelvin. Reminding myself that these are significant. Alright, so now I can do some really simple math. 735 times 158 times 358.15 divided by 108 divided by 307.15. My pressure should be equal to 1253.819, and I'm going to round that to 3 sig figs. So 1250 millimeters of mercury. Notice I cancel my kelvins and my milliliters, so millimeters of mercury is all that's left over. Alright, let's try another one. Calculate the volume occupied by 0.845 mole of nitrogen gas at a pressure of 1.37 atm and a temperature of 305 Kelvin. Okay, so let's look and see what we got. They want to know, calculate the volume. So volume is equal to what? They don't tell us what they want the volume in, so just put a question mark. They do give us mole. Mole is N. 845 mole. Pressure. They give us a pressure. 1.37 atm. And they give us a temperature, 315 Kelvin. Now, if you're not given more than one temperature, volume, or pressure, you can't use the combined gas law. Now we must be talking about the ideal gas law. And I'll remember the R for this. Let's check our units for R really quick. So it looks like I'm going to be getting my volume out in liters. I've got ATM, moles, and Kelvin, so I don't have to do any other conversions. I can just kind of plug it in. So volume is equal to nRT over P. And then volume is equal to 0.845 moles times R times T. 315 Kelvin over 1.37 atm. So I get my atms to cancel, my kelvins cancel, my moles cancel, left with liters. That's what I want for volume, so that's good. Let that unit kind of catch you through that. Then you've got simple math to do. 0.845 times 0.0821 times 315 divided by 1.37. This means my volume is equal to 15.95, which for 3 sig figs we will round to 16.0 liters. Alright, next one. A sample of gas has a mass of 0.136 grams. Its volume is 0.112 liters and a temperature of 298 K and a pressure of 1.06 atm. Find its molar mass. So remind me really quick, molar mass is equal to grams per mole, correct? So that's what I really want to find. They give me the mass, so 0.136 grams, but I need to know how many moles to get grams per mole, right? That would be molar mass. So I need moles. That's really what they're asking me for. So let's look at everything else. They give me a volume of 0.112 liters. They give me a temperature of 298 Kelvin, and they give me a pressure of 1.06 atm. And I need to know moles. Why do I need to know moles? Because I need to know molar mass. Molar mass is grams per mole, and they have given me grams. So I don't need to find that out. So it looks like I'm using the ideal gas law because I don't have more than one of anything. But this time I'm solving for N, so it's PV over RT, which in this case is going to be 1.06 atm multiplied by 0.112 liters over R, which is 0.0821 liters times atm over moles times Kelvin times T, which is 298 Kelvin. My Kelvin cancels, my liters cancel, my atm cancels, 1 over 1 over mole is mole. So that's good, that's what I want. So if I do some simple math, I get N moles is equal to 1.06 times 0.112 divided by 0.0821 divided by 298. Moles are equal to 0.00485249. I'm not going to round anything yet because I'm not done. I want molar mass, and mass is equal to 0.136 grams. Now I'm going to plug my moles in. See what that equals. So 0.136 divided by 0.00485 28, sig figs are 3, 28.0 grams per mole. Then I could probably use the periodic table to figure out what that would be. It looks like it's going to be a nitrogen molecule. 14 plus 14 is 28. So that could be that. That's a guess. So you can identify as well. This question's not asking me to do that, but I could identify which of the following, like on multiple choice, which of the following gases, would this sample be? And you could say like, oh, like this is probably N2 because it's two 14s together. So here is a quick rundown of all these different relationships, variables and constants, and they're the names of the laws and their relationships. But again, if you just remember combined gas law, the real combined gas law with N in it, and then the ideal gas law, you'll have everything you need. There's one more law called the Daltons Law of partial pressures. This law really just states that the total pressure of a gas is equal to all the partial pressures of all the gases that are combined in this total sample. Which makes sense, right? So the total pressure is equal to all the combined partial pressures. So let's look at this example. A mixture of helium, neon, and argon has a total pressure of 558 millimeters of mercury. If the partial pressure of helium is 341 millimeters of mercury, and the partial pressure of neon is 112 millimeters of mercury, what's the partial pressure of argon? So they give us the P total is equal to 558 millimeters of mercury. Then they give us the partial pressure of helium. We write that PHE, 341 millimeters of mercury. And the partial pressure of neon, PNE, 112 millimeters of mercury. What's the partial pressure of argon? Well, Dalton's law of partial pressures says the total is equal to all the parts. Okay, so 558 is equal to 341 plus 112 plus pressure of argon. And so I can say the pressure of argon is just going to be simple 558 minus 341 minus 112 must be 105 millimeters of mercury. If you need some help with that algebra, let me know. We can go over some of that as well. Okay. All right. Now, sometimes we're going to be using vapor pressure. So vapor pressure is, and whenever you've got like a bottle of water, there's always a little bit of that water that's turning into water vapor at the top. So if you put your bottle of water in a hot environment for a long time and you open it, you'll hear a ch sound, right? So that means that the water is constantly going into this vapor state. So at a certain temperature, the vapor pressure of water increases as you increase temperature. That means that the hotter it is, the more the particles are moving, and the more they're kind of jumping into that gas, that vapor state. So we can say that if we've got some water and we're creating some gas from a reaction and capturing it, we can calculate the pressure of this gas by taking the total pressure inside the tube minus the vapor pressure of the water that's inside the tube. So that kind of doesn't make a lot of sense, but let me just kind of maybe draw you a picture. So let's say I'm doing a reaction, okay, and I'm creating some gas, but I'm collecting it in a tube, and there's water in this tube. So in here, in this gas right here is equal to water vapor, because anytime you have a container of water with a little bit of space in it, you're going to have water vapor, plus your gas of interest, whatever we're making in this chemical reaction. Now, the pressure inside the tube likes to equal the pressure outside. Okay, so when they give us this total pressure right here of 758 millimeters of mercury, and they give us a temperature, we can find the partial pressure of the hydrogen gas as the gas of interest. So they tell us, we actually look it up, we can look at here, 25 degrees C is 23.8 millimeters of mercury for my water pressure. So they give us a total pressure of 758 millimeters of mercury. They give us a partial pressure of the hydrogen gas. They want us to find that. And they tell us the PVAP, the vapor pressure of water, is 23.8 millimeters of mercury. So what is the pressure of the hydrogen? Well, it's going to be 758, the total pressure, minus the vapor pressure of water. Whatever is left over is going to be my pressure of the hydrogen gas. So anytime you do any reaction where you collect a gas in a tube, you're going to be doing this Daltons Law of partial pressures in your math. So I have 758 minus 23.8 is equal to 734 with my sig figs. Millimeters of mercury is my answer. Alright, so one more thing about gas laws is that, of course, with anything in chemistry, we can relate everything back to moles. If you can relate to moles, you can do a stuff with a chemical reaction. So this question asks, how many moles of ammonia are formed by the complete reaction of 2.5 liters of hydrogen at 381 Kelvin and 1.32 atm? Assume there's more than enough N2 nitrogen. So they're telling us the limiting reactant is hydrogen. The first thing I need to do is to write a chemical reaction. So they're telling me hydrogen plus nitrogen yields ammonia. I have to balance this, so a quick balance gives me this. Whoops. A quick balance gives me this. Okay. Then I can put in some information. So I want to know how many moles of ammonia. They give me 2.5 liters of hydrogen. The hydrogen's at 381 Kelvin and 1.32 atm. Okay, so I need to find moles of hydrogen. Do you see why? Because moles of hydrogen, how many moles of hydrogen in a mole ratio here? Equals some moles of ammonia. 3 moles of hydrogen is equal to 2 moles of ammonia. That's going to get me where I want to go. So I have to find moles of hydrogen. So if I'm being given a volume, 2.5 liters, I'm given a temperature, 381 Kelvin, and I'm given a pressure, 1.32 atm, and I want moles, well, that's going to be the ideal gas law. moles are equal to PV over RT. 1.32 ATM times 2.5 liters over R times temperature in Kelvin. Okay. If I look at my units here, ATM will cancel, liters will cancel, Kelvin will cancel, moles are what I'm left with, or 1 over mole, which is mole. So my answer for moles, that's not my total answer, but my first little answer is going to be 1.32 times 2.5 divided by 0.0821 divided by 381. So n is equal to 1.1. The sig figs are 2 here, 0.11 moles. I can probably not round. Let's not round yet. 1053704 moles. Okay, so that's how many moles of hydrogen. That's how many moles of hydrogen, not ammonia, which is what I'm asked for. So for every 3 moles of hydrogen, I make 2 moles of ammonia. Now I can get my answer, so I'm going to multiply this number by 2 and divide it by 3. And I'm going to get 0.070 moles of ammonia as my final answer. Alright. The last thing here in this chapter is called molar volume. We've seen this before, but we haven't covered it yet. Now is the time. The volume occupied by 1 mole of a gas at STP is 22.4 liters. STP is standard temperature and pressure, 0 degrees C, which is 273.15 Kelvin, and 1 ATM. That is standard pressure and temperature. If you're not at that temperature and that pressure, you're not at STP, you cannot use this. This is only for gases. So, don't use this for liquids or aqueous solutions either. This problem is not at STP, right? We're at 381 and 1.32 ATM. That's not at STP, so I have to use ideal gas law. If I'm at STP, though, I can use the molar volume, 22.4 liters, is equal to 1 mole of a gas. So it's really helpful for me. So last question. Calculate the number of liters of gas that forms at STP when this many moles of calcium carbonate undergoes this reaction. So I can take this many moles of calcium carbonate and I can figure out how many liters of carbon dioxide gas. So first, we're going to use a mole ratio, right? So for every 1 mole of calcium carbonate, I make 1 mole of carbon dioxide. If I'm at STP, 1 mole of CO2 is equal to 22.4 liters of that gas at STP. That's the only reason I'm able to use this shortcut. If they didn't give me STP, if they gave me a bunch of other information, I'd have to use the ideal gas law. You have to get moles and then use ideal gas law. 0.879 times 22.4 would be equal to 19.7 liters of CO2 for this question. Alright guys, that is chapter 11. And let's see. Get out of this.